Hello my dear friends, welcome to this online class. In this video, I am going to frame the partial differential equations by eliminating the arbitrary function. So, elimination of arbitrary functions. Elimination of arbitrary functions. Already we have seen that there is one more technique. We find the partial differential equation by eliminating the arbitrary constants. But suppose there are any arbitrary functions, then how to eliminate those arbitrary functions, which we will get the required partial differential equation. So that is the concept behind this topic. It's clear. The hint before going to start with this topic, in the given relation, in the given relation, the number of arbitrary functions, only one. Then while eliminating the arbitrary function, we get the first order PDE. Suppose we have more than one arbitrary function, then we will get, while eliminating those arbitrary functions, we get second or higher order. We get the second or higher order. So this is the hint before going to start this topic. Elimination of arbitrary functions. Elimination of arbitrary functions. So this is the idea. It's clear? Let us see. So let us see the first problem. Problem number 1. Problem number 1. Z is equal to a function of x squared minus y squared. Suppose if I am going to consider z is equal to f of x squared minus y squared. So this is the given relation. So there are no arbitrary constants. Only one arbitrary function f is there. So how many functions? Only one. So by eliminating the arbitrary function, we get the first order partial differential equation, isn't it? So if it is a first order partial differential equation, then how many times we differentiate? Only one time. So let us see. I am going to differentiate equation number 1 partially with respect to x and y. Partially with respect to x and y, we get the left hand side is with respect to x. So dou z by dou x. Right hand side is a function of x squared minus y squared. So it is f dash of x squared minus y squared. By using the chain rule, if I differentiate this with respect to x, we get it is 2x. Is that right? So the left hand side is p. So p is equal to f dash of x squared minus y squared into 2x. So from this, I found that p by 2x is equal to f dash of x squared minus y squared. So this is the equation number 2. Similarly, when we differentiate the equation number 1 partially with respect to y, the left hand side is dou z by dou y. The right hand side f dash only one time, because we differentiate only one time, either with respect to x or y, because a function of x and y. So f dash of x squared minus y squared into, once again by using the chain rule to the term x squared minus y squared, this time with respect to y. So the answer is x squared becomes 0, y squared becomes 2y, but minus sign was there, so minus 2y. So the left hand side is q. So q is equal to f dash of x squared minus y squared into minus 2y. So from this, q by minus 2y is equal to f dash of x squared minus y squared. So this is the equation number 3. So there is only one arbitrary function. So while eliminating the only one arbitrary function, we get the first order. So I think so we may almost reach this answer. Let us see the equation number 2 and 3. The right hand sides are f dash of x squared minus y squared, f dash of x squared minus y squared. So from 2 and 3, what we conclude that once the right hand sides are same, so left hand sides are also same. So can we compare the 2 and 3? From equation number 2 and 3, we conclude that the left hand sides are same. So p by 2x is equal to minus q by 2y. After cancellation of this 2, cross multiplying this, we get it is py is equal to minus qx, otherwise py plus qx equal to 0. So this is my PDE of order 1, or it is first order PDE. Why this is called first order PDE? P and Q are the first order partial derivatives. Why we get first order? Because in the given relation there is only one arbitrary function. So that's why we get the first order partial differential equation. Is it right? Let us see the second problem. The second one, I can consider z is equal to f of x plus ct plus g of x minus ct. Please see that this is something is different. Z is equal to f of x plus ct plus g of x minus ct, where c is the constant. C is the fixed constant. And what about f and g? F and g are the arbitrary functions. So how many arbitrary functions are there? It is more than one. So we get minimum second or higher order. So here my ultimate aim is to eliminate both f and g. C is fixed constant. So the final answer is in terms of the constant c. Let us once again name as equation number 1. So this is my problem number 2. Now differentiate equation number 1 partial with respect to x and y. We get what we will get. Let us see. Differentiate 1 partial with respect to x and t, not y, because in this relationship z is the function of x and t, so there is no y at all. So that's why I consider this problem z is the function of x and t in this relation. Correct? Now when I differentiate z with respect to x, I don't know the function. So first time f dash of x plus cte. Once again differentiate this x plus ct with respect to x, we get 1. Once again differentiate this with respect to x, we get 1. Plus I don't know about the function g. So first time differentiation, because g is also a function of x and t. So with respect to x, we get g dash of x minus ct. Once again differentiate this with respect to x, this becomes 1. It's clear? So what is dou z by dou x? F dash of x plus ct into 1 plus g dash of x minus c2 into 1. So this is the with respect to x. What about with respect to t? With respect to t is dou z by dou t is equal to f dash of x plus cte. Now this time we differentiate this with respect to t. So what is the coefficient of t here? C. What about x? X becomes 0, because y differentiate with respect to t, x is the constant, plus g dash of x minus cte. Once again differentiate this with respect to t, we get minus c. It's clear? Is right? Is it possible now to eliminate both f dash, g dash from in these two relations? It's not possible. Why? Because there are two arbitrary functions. At least we move on to the minimum of second order partial derivative. So we once again differentiate this with respect to x and t. So once again differentiate this with respect to x. What happened? Once again differentiate partially with respect to x and t. X and t. X for this one. Okay. What happened? Once again means dou by dou x of dou z by dou x. Once again differentiate this. Second term differentiation. So f double dash of x plus ct. What about x plus ct with respect to x? Differentiation 1 plus already 1 is there, so 1 into 1 is 1, so no problem at all. And once again g with respect to x, so already one time we differentiated with respect to x, so this already g dash. So second time this becomes g double dash. Once again differentiate this with respect to x. I am getting the 1, right sir? Right. So f double dash of x plus ct plus g double dash. This is the second time with respect to x. This can be differentiated partially with respect to t. Second time, what we will get? Dou by dou t of dou z by dou t is equal to 1 time over the second time f double dash of x plus ct. Already one c was there. Already one c was there, right? One c is already there. What about the derivative of x plus ct with respect to t? So t becomes 1, so c only. So one more c. So c into c, c square. Similarly, plus g double dash of x minus ct. Clear? Already minus c was there. Please see that minus c was there already. Once again differentiate this with respect to t. I get one more minus c. So minus c into minus c whole square or plus c square. It's clear? Still my aim is to eliminate both f and g or f dash g dash or f double dash g double dash. I don't want this any f and z's. So in this equation number, this in this side, what we think that dou into dou, it is dou square z by dou t into dou t is dou t square is equal to. I think so here we have c square. What about here? Minus c whole square. So minus c whole square plus c square. So I can take c square is a common. Right? So what is the rest of the terms? It is f double dash of x plus ct plus g double dash of x minus ct. Is right? I need the value of this term. I would like to use the other side. So in this side, what about f double dash of x plus ct into 1? It is f double dash of x plus ct only. And g double dash of x minus ct into 1 is g double dash of x minus ct. So what about this value? This is nothing but dou by dou x of dou z by dou x. Otherwise, dou square z by dou x square. So can I use this instead of this? I am getting that it is equal to c square into dou square z by dou x square. So for your reference, I can name this is my equation number 2. So from equation number 2, I am getting that c square into dou square z by dou x square. Right? So what about c? C is a fixed constant. So by this way we get dou square z by dou t square is equal to c square into dou square z by dou x square. So there are no arbitrary constant. This is my required partial differential equation of order 2. So it is the second order partial differential equation. Got it? Now, this is the general problem. Because here c is called a constant. Here c is the constant. Suppose in the case of constant, if there is any specific value or particular values are assigned to c, what will happen? See, I am going to consider c is equal to 2. Suppose c equal to 2, now this becomes x plus 2t g of x minus 2t. So the same problem in terms of c we already did. The answer is dou square z by dou x square is equal to c square into dou square z by dou x square. Now in the place of c is 2, so again we can proceed the same manner. Finally replace c by 2. So what is the answer for this? PDE dou square z by dou t square is equal to 2 square into dou square z by dou x square. What is 2 square? 4. That's it. Suppose If I consider the C is equal to I, suppose C is equal to I, what happened in this equation? This equation becomes Z is equal to f of x plus it plus g of x minus it. So the same problem, we can assign different values to the constant C, right? Different constant to the values to the constant C. Suppose C is equal to I. Once again, what will be the answer? Dou squared z by dou t square. Dou squared z by dou t square is equal to I square into dou squared z by dou x square. What is the I squared value? It's a complex number. I squared is minus 1. So what we will get? We will get it is minus 1 into dou squared z by dou t x squared. So by that way, it is we are getting that dou squared z by dou t squared plus dou squared z by dou x squared is equal to 0. So this is the required answer for when C is equal to I. Suppose C is equal to 2, this is the order, this is the required second order PDE. Generally, C means this is the answer. So this is the common problem. So as an exam point of view, if the C value is given to you, you can do like this. Finally replace C value, the corresponding C value, will get the respective partial differential equation. Why you will get the second order? Because of there are two arbitrary functions. So this is the simple hint for you. Got it? I think so. You may understand this. The elimination of arbitrary functions. One function in the given relation, then we get the first order. If there are two arbitrary functions, then while eliminating, we get second or higher order PDEs. We try to get within the second order. Okay. Thank you so much. Thank you.